Hello once again, people. I'm the heavy metal chemist, and I'll apologise for the delay in this, but new job, Christmas, and various other things got in the way. So I'm going to do a bit of a change up from doing organic reaction mechanisms tonight, and I'm going to cover something called the ideal gas law, which is a bit more of a physical chemistry thing, but it's fairly quick and easy to go over, but it's still fairly useful. So what this is a very simple equation, which is PV equals nRT. This is where P is pressure, V is volume, N is moles of gas, R is a constant called the ideal gas constant, and T is temperature. Now the units of these: pressure is in pascals, volume is meters cubed, the moles of gas is in moles, which would be mole. The temperature is in Kelvin rather than degrees C. It's the same size of unit, but this starts from absolute zero rather than zero being the freezing point of water. And the constant is, I believe, 8.314. Yes, it is. It's 8.314. And that's the units of that are joule per Kelvin per mole. So basically what this does is it tells you that if you've got an amount of gas, say 1 mole, and you know the pressure and the volume, it'll give you the temperature. Or if you know the temperature and the volume, it'll give you the pressure, and so on. So basically we can use this to calculate the amount of space a mole of gas will take up under ambient conditions, for instance. So basically what we do, if I do this as an example, if we take V is what we're after, so we'll just divide all of that crap by the P, so V equals nRT over P, which will equal, sort my pen out, 1 for the number of moles, times by R, which is 8.314, times by the temperature, which at standard conditions is 273 Kelvin, that's 0 degrees C, or for instance that could be 298, which would be average room temperature, say 25 degrees. And standard ambient pressure is generally accepted to be 1013 kilopascals, which should be 1013000. Now if I quickly run that into the calculator on my computer, what that gives us is 8.314 times by 273, I'll do it for the 0 one, divide that by 101300, added one too many zeros there, and what that gives us is the grand total of 0.022 meters cubed. That's in meters cubed, no, not litres. Therefore a mole of gas takes up around about 22.4 decimeters cubed, which is litres. So at standard temperature and pressure, a mole of gas, this is any gas, the ideal gas law applies to all gases no matter how heavy they are. So above 100 degrees it could be steam, although steam is far from an ideal gas because this formula assumes certain interactions between the molecules which you can't easily replicate in a formula. So it works fairly well for things like helium, the noble gases, helium, krypton, neon, argon, etc. And some of the diatomic gases, so carbon dioxide, that's triatomic, nitrogen, oxygen, things like that, the more volatile things. And basically what you can get with this is what's called an isotherm. So if you draw a graph of, say, volume and pressure, you end up with a series of things like this, which are plots of various different temperatures. T1, T2, T3, as it gets hotter it moves further up. So I hope that provides a rough idea about that. Basically you can rearrange this this is the key bit. I'm not going to go through all the various permutations because I'm assuming that you all know algebra if you're studying chemistry. And that's something I really don't want to have to go into, but if it's requested, then I suppose I could cover it. So thanks for watching. Hope you all had a good Christmas and have a happy new year. Please do like this video, share, comment if you've got any constructive criticism, etc., etc., and I shall hopefully see you soon. Thank you and goodbye.